we have a point. This one's kind of interesting. A point P lying on a segment AB. So I might want to move this segment a little bit. Sorry. So I'll call this P. And so we have two circles that are tangent to AB at P. So here's one circle and here's another circle. And then we draw the tangents from A and B to each of the circles. So something like this. And then we label the 4 points. So this is A1 and A2. And the others are B1 and B2. And we draw so basically the radical axis of these two circles. So A1, B2P and A2, B1P. So L is the radical axis of those circles. Let me draw their intersection. Okay. And okay, basically we want to show that PE, A1, A2, and B1, B2 concur. So we want to show A1, A2, and B1, B2 concur on PE. All right, so I'm going to hide some stuff. I drew this line right here so many times. I'm not even going to try hiding it because the tangents. Yeah. Should I even keep the center? I'm going to hide the centers of the circles for now, just to make it easier. So we want to show, yeah, A1, A2, B1, B2, and PE are concurrent. Actually, yeah, I'm going to hide this. So I'm probably going to have to hide it a couple times. There we go. I think one more. There we go. Yeah, it's not that complicated of a configuration, which is kind of nice. But yeah, we could check that it's true. Oh, that doesn't look right. What did I do wrong?
You should draw the perpendicular from P to the AB.
Oh, the circumcenters, my bad. I thought L was the radical axis. Never mind. It's the line through the circumcenters. So yeah, let me just use the midpoint thing. Whoops, that was the wrong circle. So yeah, we want to show A1A, yeah. Interesting. So is maybe the SARGs is a way to do it? I'm not sure. The SARGs is kind of my first thought when it comes to concurrency, but sometimes there's an easier way. Yeah, with all these tangent lines, like maybe Monge's theorem does something. I don't know. So how would we apply Desargues' theorem? I feel like there's usually like whenever there's a concurrency, isn't there like always a way to use Desargues? I just don't see it here. But I wonder if I guess we're saying that GB2A1 and FB1A2, we want to show that those are perspective. What is that? Yeah, no, I think what Hakan said is right. So let me just it is. I just have to figure out how that translates, how we can use the SARGs then. So GB2A1 and FB1A2. A2B2 and A1B1. Yeah, that's could be. Let's move the diagram around a little bit. So it looks like they are concurrent. Yeah. Interesting. Is A2, B2, B1, A1 cyclic? Yes. So maybe we show they're concurrent and then we use power of a point or something like that. Let's see, A2, FG, B2. No, that's not cyclic. are GB2 and GB1 tangent to that circle? I think you mean GB2 and FA2, right? Kind of looks like it. Yeah, I think so. Let's see.
We can prove this. We can use Brocard.
Use Brocard to prove it. Okay.
No, actually, if we can prove this, we can use Brocard.
Oh, okay. Yeah, no, I agree. I'm gonna hide A2, B2. Yeah, because I wanted to see, I'll just draw the point of concurrency right now. I don't think AB passes through that, right? Oh, it does. Huh, interesting. I'm not sure what we've proved and what we haven't. But is that an easy angle chase? Let me hide a bunch of stuff.
Well, we didn't concurrence of 3 lines.
We haven't yet shown that they concur, right?
Yeah, there are 4 lines that concur.
Okay, what? Let's see. Yeah. So wait, that's not true that A, B1, and B2 are collinear. That must just be a coincidence. Oops. Yeah, okay, so I'm gonna erase that line. So basically we want to show FG is the polar let's see, A1, A1, B1, AB, and A2, B2 concur by the radical axis theorem. So if we take, yeah, we didn't prove yet that that's cyclic, but if it was, is FG the radical axis? So if we look at the point circle P, oh yeah, yeah, okay, so yeah, no, once we prove that, it would be true by the radical axis theorem. Oh, really? That's interesting. That those three are concurrent. Let's see. Oh, no, they're not. I was gonna say that would be really cool. But yeah. We'll be right back, guys. All right, thanks for waiting. Okay, so you can prove that A2, B2, A1, B1, and AB are concurrent by harmonics. Because A, B, P, and H are in harmonic conjugation. How do we know they're in harmonic conjugation?
A1, B1 is in circle.
Because this is the end circle. It's like the Dragone point, but yeah, okay. So A, B, P, and H are in harmonic conjugation. So yeah, so that makes sense. So A1, B1. Okay, so yeah, so then A1, B1, and A2, B2 have to concur at H, and then you could use power of a point to use that to show that A2, A1, B1, B2 is cyclic. That makes sense. All right. And then once we're there, is it just like, so we still have to show FG passes through H, right? So it looks a lot like Ricard's. So, I mean, basically we could draw the intersection of A1, A2, B1, and A1, B2. And we want to show that the line FGH is the polar of that point, right? An inversion at H takes A2, B1P. Could be. So with radius HP. So what if let's see, I reflect, let me try, let's see, let me draw that. So oh, does HP equal HE? Or is that obvious? I'm not sure. But yeah, so I'm going to try the inversion. So if I reflect this circle about this, then I get the other circle. Yeah. Is that obvious that it swaps them? So obviously it fixes P because
Michael, I think in inversion at H will solve this problem.
okay.
Okay, so we know that if we do the inversion at H with the what
Gradient.
HP square. Yeah, so it will take A1 to B1, A2 to B2, and the same to B2 and B1, and it will keep P at P. So the circle A1 B2 P will become A2 B1 P. Yeah, so F and G will collinear to H.
So F and G have to be collinear with H. Yeah.
Yeah. And after that we can prove that if we call A2A1 cut B2 B1 at a point.
Whoops, sorry about that.
Yeah, so yeah.
I could call that point. Yeah, I'll call it I.
Okay.
Or how about J, just because so I don't think it make it to end center or something. All right.
Yeah. So hold on. Just
right.
wait for a second.
No rush. Yeah, we proved that F, G, and H are collinear by the inversion. But we have to show that J lies on it. So once we know that this is cyclic, did you say we could show FA2 is tangent to that circle?
What?
Can we show that FA2 and FB1 are tangent to the circle?
I don't know.
I think so, because then I think it would be true, because then basically we could show FG is the polar. So basically, if we intersect these two at a point, then we could show that F lies on the polar of that point, and G also lies on the polar of that point. So that would mean F, G, J, and H are all on the polar of this point. So yeah, we have to, if we can show FA2 and FB1 are tangent, that would solve the problem.
How did we prove that F, G, and H are collinear from inversion?
So basically we showed that an inversion centered at H swaps these two circles. And so since F and G are the centers of them, H has to be collinear with them. Because yeah, so consider an inversion at H with radius HP. So it sends P to itself. And then since HP squared is HA1 times HB1, it swaps A1 and B1. And similarly, it swaps A2 and B2. So if you combine all that, it has to swap these two circles. And so if it swaps two circles, then it has to be collinear with their centers. Yeah. I don't even think you really need point E. Like, I guess that's one way to, like, but like if an inversion swaps two circles, it has to be collinear with their centers, right? By symmetry. So yeah, we just have to show FA2 is tangent to the circle. I don't know if that's just like an angle chase. So yeah, we'd want to calculate angle FA2B2. Yeah, I'll label the center of it. What K? So basically we want angle FA2K to be 90 degrees. That's one way to say it. I wonder if PE and K are collinear also. Yeah, so it looks like it. Interesting. So PE and K are also collinear. Yeah, it seems like it shouldn't be. First of all, is it true that FA2 is tangent? Oh, okay. FA2 equals FB1. KA2 equals KB1. And KF is perpendicular to A2B1. No, not necessarily. That only implies tangency if the circles are orthogonal. So I don't know, have you heard of orthogonal circles? So this is interesting. So if we do the inversion at H, it swaps this circle with that circle, but it fixes this circle. Yeah, this orthogonal circles are where this angle is 90, so FA2K. So if we could show EP passes through K, and we could show KA2 squared is KE times KP, then that would solve. So KA2 is equal to KB2. So basically we want to show that angle. There's a bunch of different ways to think about it. Maybe invert at K with radius KA2. Interesting. So we want to show that takes swaps E and P. I'm not sure.
Michael.
Mm-hmm.
If we call if we let the perpendicular from P to JH,
Okay.
cut JH at one point.
All right. Hold on a second. So, so basically PK is per. Okay. So I think it's just. I'm gonna kind of cheat here. Yeah. Let me make it a little bigger. Just sorry.
Can we prove that J is collinear? JP is perpendicular to AB.
Interesting. I'm
Could
not
we?
sure. Let me draw this point. The point you mentioned though. I'm just trying to make it bigger. Right here. There we go. Call it L. Whoops. Sorry. I just had to make it bigger. Okay. So L is the perpendicular from P to FG.
Yes.
Oops, sorry. Whoops. There we go.
So if we can prove JP is perpendicular to AB.
Mm-hmm.
Yes. So we will have H L times HJ is equal to HP square.
Ah, I see what you're saying.
So L will be the Michael point, right?
Mm-hmm.
Yeah. So KLPE will be collinear.
All right. So we want to try to show that JP is perpendicular to AB. So
Yeah.
L would be the McKell point of this quadrilateral, A1, A2, B1, B2.
Yeah.
All right.
But only if we can prove JP is perpendicular to AB.
All right. Interesting. There's a lot going on here. But yeah, I feel like there has to be a way to show FA2 is tangent to this. So, I mean, so we know FH is perpendicular to EP, but basically L is the intersection of EP with FH. We know that to be true, right? Because we know FEPH is a kite. Whoops.
No, we don't know JF and H is collinear. No,
Yeah, we don't know JF and H are collinear, but we know that PE is perpendicular to FH, right?
Yes, yes.
So basically we want to show if L was the McKell point, then we would have a couple cyclic quadrilaterals, I think, right? Yeah. L is the midpoint of EP. Yeah. We just don't know that J lies on that line. Yeah, I just feel like it shouldn't be hard to show that FA2 is tangent. So yeah, if we could show KA2 is tangent, that's the same thing. So yeah, what if so yeah, I could try to do an inversion centered at K with that radius. J is the intersection, yeah, of A1, A2, and B1, B2. We don't know it lies on this line, so I know it's a little confusing. So what is the same inversion centered at H? It swaps these two circles, but it fixes this one. Yeah, we want to show they're orthogonal. I wonder if AF2 and BG2, no, I don't think those meet at anything special. We want to show those are tangents. E2AJ. We know JP. No, we don't know that yet. Unless you can think of a way to prove it. Oh, really? Inversion with radius. Interesting. Wait, how would that? Let's think. Yeah, let me know. So, yeah, how would that inversion prove it? Let me know if you can think of how it would work. Oh, okay. Spend like 5 more minutes on this one. So yeah, do we know that PE and K are collinear? Actually, that would solve the problem if we knew they're collinear. Or what you were saying, A2J, LB2. Oh, once they're collinear. Okay. Yeah, but we don't know that KA2 is tangent to this circle. So how would we do? So that inversion, it would fix those points. It would swap P and E. So we know PE is perpendicular to FH. Maybe we could show PK is perpendicular to FH. Not sure. Yeah, so ultimately we want to show FG as like the polar. So I haven't used, so FK is perpendicular to A2B1. I think we're close. L. So I'm wondering if there's some kind of angle chase thing. Because maybe we want to use this tangency again, I feel like. So angle FA to B2. That's FA to A1 plus A1 A2 B2. All right, you guys want to move on to the next problem or just take a look at it?
Yeah, let's move on.
All right. Okay, so we have a triangle ABC with orthocenter H. Whoops. And we draw the theta altitudes from B and C. Whoops. It's E and F, and M is the midpoint of BC. All right. H, M is the midpoint of BC. Delete these two. You draw the perpendiculars from M to each of those sides. It's X and Y. So X is the midpoint of BF and Y is the midpoint of CE. And I feel like we have a Varignon parallelogram. Like if we take the midpoint of the EF, we'd get a parallelogram. X, Y, and EF meet at P. And I wonder if P lies on BC. No. But they meet at a point P. And Z lies on XY, so that AZ is perpendicular to HP. Okay. So we want to show AZM plus HPE is 180. All right. So I'm gonna label the mid. I'm gonna hide some stuff, but I'm gonna label the midpoint of EF, just because dx my is a parallelogram. What is Z? AZ is perpendicular to HP. Okay. So I might want to unhide this and just draw the intersection point and then hide it. So we want to show AZM plus HPE is 180. So yeah, we could just say X and Y are the midpoints of those two. We have a parallelogram here. I don't think Z is the midpoint of XY. I think it might be. Yeah, it looks like Z is just the midpoint of XY. So just the center of that parallelogram. So we could start out proving that. And then once we prove that, so we could let Z be the center of this parallelogram. And then we want to show that AZ is perpendicular to HP. That doesn't seem so bad. I'm trying to see if I can show H as an orthocenter. So like, what if, that seems like a pretty fundamental fact that AZ is perpendicular to HP. We use like Ricard's or something. So basically we want to show angle AZB is HPE. So basically we just want to show PBGZ is cyclic. And that I think might just be obvious because wait, yeah, so that's actually obvious. So yeah, once we can show the thing that I said, yeah, once we can show that AZ is perpendicular to PH, then that solves the problem. So could we use, maybe we could show, let's see. Yes, exactly. So Z, it's the midpoint of XY, it's the midpoint of DM. Yeah, exactly. What if we, I was wondering if we could show H as the orthocenter of another triangle, although I'm not sure. So yeah, we have a lot of midpoints here. I don't know if we could use the gliding principle somehow. Yeah, is PG parallel to something? Yeah, what can we say about AZ? Or is there anything else? Like, what if we draw the perpendicular from M to AZ? Or so we know, yeah, we know MB is perpendicular to EF. So hold on a second. HP is perpendicular to AC. Maybe vectors would help or something like that. Yeah, I want to use Bricard's theorem also. So if we extend EF and BC to meet at a point, like what if I did that? So I think that might make things a little bit easier. Let me extend EF and BC. And then if we call that point, let's see what it's called. If we call it J, then we have JH is perpendicular to AM. And we want to show PH is perpendicular to AZ. So what if so we want to show JHP, angle JHP is angle MAZ. Whoops. Sorry, it has to go (4.1). Dang it. But yeah, it should be 4.1 also. Yeah. Is triangle JHP similar to MAZ? I don't think so, but it's possible. Oh yeah, we want to show JHP is similar to MAZ. So what if we reflect J across P? So we want to show DAM is similar to JJ prime Z. I don't know if that does much. So X is the midpoint of PF. I'm sorry, BF. So is it true that JP, okay, so yeah, JP is perpendicular to MZ, we know that. And we know JH is perpendicular to AM. So we know that 2 of the 3 sides are perpendicular. So we know that angle PJH is ZMA. I think we know that. Wow, this is hard. Seems like a simple problem, but it's not, I guess. So we want to show PJH is similar to MAZ. Is it worth drawing the Humpty point? Let me try it. It's so basically I'll draw the circumcircle of BHC. And it should pass through that point. Yeah. Let's see. So we have HI is perpendicular to AM. And we want to show HG is perpendicular to AZ. Which is the same as showing yeah, so if that were true, we would have like all these points on a circle, right? So maybe we could draw this circle and we could let G be this point, and then we want to show, I think it's easier to do that. Then we want to show EF, GH, and XY are concurrent. I like that approach better. So let's even delete point P for now. So, or hide it. We want to show EF, XY, and GH, or sorry, EFXY and GH concur. We use the SARGs. So we want to show FHX and EGY are perspective. Can I let HGZ cut XY at a point? Yes. I let HG meet XY at a point. So yeah, HG would meet XY at that point that we just had, right? Hold on. Oh, are you trying to use the radical axis theorem? Okay. Okay, so that point's harmonic with X, Y, and J. So basically that means X, E, Y, F, and AJ are concurrent. But we would want to show that. Maybe that's just Cheba's theorem. FHJX. Yeah, so FEJ is like the pedal triangle. I wonder if are G and H. No, they're not. What do you call it? Isogonal conjugates. So you're trying to show FEJZ is cyclic, basically. AXYM. Oh, whoops. FEZJ. The 6-point circle of AXY. I'm not sure. I don't think so. Well, FEJ is a pedal triangle of H. That's true. Yes. And isogonal conjugates have the same pedal circle. So maybe we want to find the so the orthocenter, well, yeah. So there's some point here, which is like the isogonal conjugate of H. Okay, yeah. So that would be, let's try to do this as quick as I can. Yeah, exactly. That's what I'm trying to do. So no way XY passes through the center of the circle. Yeah, there we go. Okay, so basically this point right here should be the isogonal conjugate of H. Point N. So you said earlier that K, X, Y, and H are in harmonic conjugation. Or K, X, Y, and J. And we know Z is the midpoint of XY. So maybe so that means Kx times Ky is Kj times Kz, right? So basically, that means XHGY is cyclic. Wait, let me think about that. X. Are you sure those were in harmonic conjugation? Or no, I think that would mean Kx times Ky is Kz squared, right? Oh, okay. Or no, sorry. Projecting through E. So we want to show FJZE is cyclic. Could we do some kind of homothety since X is the midpoint of FB? Maybe use the gliding principle or something. Like what if we did a homothety of that circle about D? Yeah, let me think about this. We want to show if FJZE is cyclic, that solves it. If that were true, would D be the center of that circle? Let's see. No. So the center would lie on MB. It would lie on MD and it would also lie on HN. It would be the midpoint of HN. So basically where HN intersects MD. Oops. Interesting. Let's see. Yeah, this is such a weird problem. It's like XY's line passing through the midpoints. We have the midpoints of three segments, BF, DM, and CE. So if you draw this point's collinear with H and M, and OFE is similar to OXY is similar to OBC. So yeah, spiral similarity at O. So OH and M are collinear. That's well known. And the spiral similarity takes OFE to OXY to OBC. then AOXY is cyclic? I think so. Yes. And it looks like it also passes through M. Oh, and I think that might be true by the gliding principle, actually. Let's see if it really passes through M. Yeah. Interesting. It's a circle with diameter AM. Yeah. Yeah, it's more obvious than I thought. So maybe that might make the radical axis theorem a little bit easier to apply. So are AO and K collinear? I don't think so, because I think that would pass through a different point. Yeah. Yes, O is the center of the spiral similarity taking FE to XY. That's true. KOXF would be cyclic. Okay, so we would define EF and XY. Yeah, I'll hide HG. I think I have to do it this way. Hold on a sec. There we go. Is H the orthocenter? Oh no, it's not. Yeah, I'm not sure how to finish this off. You guys want to just take a look at the last problems, or maybe we could use them for the session after. What do you guys think?
I have a solution for the previous
Problem?
Yeah.
All right.
Okay, so so I will prove that KB2 is tangent to the circle PA1 B2.
Okay.
Okay, we use angle chase.
Okay.
Okay, so we need angle KB2A1.
KB2A1.
Yeah, is equal to A1 P B2.
Okay.
Okay, but we have that angle KB2A1 is 90 degree minus angle A1 A2, B2.
Okay, A1, A2, B2. So you said K, B2, A1 is 90 minus, maybe I'll just type it out. So, hold on just a second. Okay, so basically we want to show K B2. I think where you saying, sorry, K B2 A1. So what were the two angles that you said you wanted to do to show it was tangent? I think it was B2 PA1, right?
Yeah.
Okay.
Yeah, but angle K B2 A1 is 90 degree minus angle A1 A2B.
Let's see. So K B2 A1 is 90 minus A1 A2 B. Let's see. Just
Yeah,
like that.
Yes, that is because A1 A2B is a half of A1 K B2.
A1.
K is the center.
Oh, do you mean A1 A2 B2?
Yeah, A1 A2 B2.
Oh, sorry.
Yeah.
Okay. So A2 B2, and then B2.
So we need to prove that angle B2 A1 plus angle A1 A2B is 90 degree.
Okay, hold on one sec. So we want to show. Sorry, I get confused a little bit. K B2 A1.
K the center. So K B2 A1 is 180 minus A1 K B2 and divided and over 2.
Okay, so it seems like it's a pretty easy angle chase, I think, right?
Maybe. So we did angle B1 P A1 plus A1 A2B is equal to 90 degree.
Okay. So okay, so we want to show A1 A2 B2 plus B2 PA1 is 90, right?
Yeah. Okay. Yeah.
And
Yeah. And we will do the angle chase. Okay. So A1 P B2 plus B2 PB plus A1 PA is 180, right?
A1 PB2 plus A1 EB2.
No, A1 BA.
A1 BA.
Yeah, plus B2 BB.
B2 PB.
Yeah, it's 180.
So A1 PA or B2 PA plus B2 PB. So the sum of these three angles is 180 basically. A1 PA, A1 PB1, and B1 PB2, right?
Yeah, and angle B2 PB is equal to B2 AP because BB is tangent.
Oh, okay. All right. So let's see how much of this I can write down. So we have this, so we start out with this. Sorry. So KB2A1 is 90 minus A1 A2B2. Okay, yeah, that makes sense. And then we could try to find angle A1PB2. So angle A1PB2 is A1. Okay, so that's angle A1PB minus angle B2PB.
No.
No.
It's 180 minus B2 PB. Yeah, and minus A1 PA. 1 PA.
B2 PB minus A1 PA. Okay.
Yeah.
A.
Yeah.
And
Angle B2 PB is equal to B2 A2 P.
B2 A2P. Okay, yeah, B2 A2P. So A.
Yeah, and B2 A2P is A2 B2 A2 A1 plus A2 A1 A2P.
Okay.
Yeah, so it would be 180 minus B2 A2 A1.
A1 minus A1 A2P. P minus
A1 PA.
A. Okay.
Yeah. Okay. So yeah. Yeah. So we need to prove that A1 A2P plus A1 PA is 90 degree.
Okay, so rearranging, basically we want to show that, say that one more time.
Yeah. So we will use KB2 A1 is 90 minus A1 A2 B2. Yeah. So
A1 A2 B2. Yeah.
yeah. And so if we and then we have this. Yeah. So if we want to show that A1 B2 is equal to KB2 A1, right?
Mm-hmm.
Yeah. So we need to prove that A1 A2P the two last.
A1 A2P. So these two.
Yeah, it's both of them. They have the total is 90 degree.
Okay, so A1 A2P and A1 PA.
Yeah,
We
that
want to
is
show those out at 90.
yeah, that is obvious because A2 is equal to A1 is equal to AP, right? So A2, A1, and P is lie on a circle with the center is A.
So hold on one sec. So sorry. Basically, you're saying,
yeah.
Yeah. So I'll also say, okay, so using the fact that A is the circumcenter of A2AP, A2A1P.
Yeah.
We find those two angles are equal, so KB2A1 is equal to A1PB2, and so that means that KB2 is tangent. Okay, so I'm just going to write this out quickly because I know we ran out of time. But so basically the idea was, so let A1, B1, and AB intersect at H. And then by extending AA1 and BB1 into a triangle, we find that A, B, P, and H are in harmonic conjugation. And then by the same reasoning, we find that A2, B2 has to pass through H. Passes through H, and an inversion at H with radius HP it swaps the circles B2PA1 and B1PA2. So that means that H, F, and G are collinear. Let me just do this super fast. So I'll just say H is collinear with the centers F and G. And then we have HB times H equals HB times HA equal to HB2 times HA2, and that means that A1, B1, B2, A2 is cyclic. Call its center K. I'm trying to do this super fast, but there we go. So KB2 is tangent to tangent to omega. The circle PB2E or PB2A1. And so I'll just say after some work by Bricard's theorem, so with some work, FB1, FA2, GA1 and GB2 are tangents to the circles. And so that means that the line, that means that FG is the polar of A1, B2, 2. And that means that FG and L are collinear by Bricard's. I'd probably FG and J. All right. So let's see how this all came out. G, see what that does. There we go. Ah, not bad. All right, so I'm going to stop right here. This is a really nice solution to the last one, so thanks, Feng. I know we went over a couple minutes. So for everyone watching on YouTube, if you'd like to join a future session, feel free to email me at mgreenv801@gmail.com. The sessions are on Sundays at 9 a.m. US Central Time. So thanks for watching and have a great day.